So welcome to the lecture number 20 for peer-to-peer networks MOOC course. In this lecture, we will be talking about firewalls, NATs, which stands for Network Address Translation Devices, and proxy, the web proxy, HTTP proxy I'm talking about, how these are actually being handled, and especially because these are used when you are going to use private IP addresses, and that becomes a problem in peer-to-peer network, because mostly you can always communicate from inside the private network to outside through either NAT or through a proxy. So how to build peer-to-peer clients, they will operate when they are inside those networks. So when a peer is behind a firewall, so for example, you can see there is a campus network here, and then there is a firewall. So this campus network is using a private IP block. So A is a peer here, P is another peer. So when they talk to each other, there is no problem. They can actually use their private IP and they can communicate with each other. But somehow they have to discover each other. And if, for example, peer A would like to communicate to peer C, which is directly on the internet, it's using a public IP address. From inside, A can actually communicate to C. But how C will communicate back to A is a problem. So A can set up either a TCP connection all the way to C. If it knows C, and then C will be able to communicate because A has created a path to this firewall. That's how the basically NAT will work. We'll talk about NAT after a few slides. Now there are peers which are directly on internet. They can directly talk to each other without any problem. The way A and B were talking, C and D also can talk. And there is a third scenario when peer B and peer E would like to talk. They both are actually in different private networks, and which are both actually being available through firewall. So if this guy uses this guy's private IP address, the internet will drop those packets. Okay. So these are basically various possible combinations of communication which can happen when the netting firewalls or proxies are used in the internet, and which of course are there. We cannot avoid them. So we have to build a peer-to-peer network which handles such scenarios. So in fact, I have listed all possible combinations: A to B, which I mentioned earlier, A to C, C to D, and A to E combination or B to E combination. So these are four typical categories which can happen. We should be able to handle these. Now in the internet, we normally use IPv4. That's very common. IPv6 also is in use now, which uses 128-bit IPv6 addresses. IPv4 uses 32-bit IPv6 IP addresses. IPv4 addresses, when designed, people thought they will be sufficient. Ultimately, it was figured out they were actually not sufficient, and there were situations when they were in short supply. So people tried classless interdomain routing in between to sort out this particular issue. They also then also, of course, even after allocating all class C addresses, it was not possible. Okay, so people then started looking at alternative ways. So that's one thing which they did was that they started with private IP addresses. Okay. Now, when we actually look at public IP addresses, each address is supposed to be used only once anywhere in the world at any point of time, and that's where the problem of shortage actually came. So we need to reuse the addresses. So there are certain ranges which were defined, which can be used in, say, IIT Kanpur, it can be used in some other institute and some other organizations. The only problem is the same IP address at any point of time exists in multiple places. How the routing is going to happen? Okay, so since multiple machines with same IP addresses are existing, so first of all, the routing rules have to be updated in all internet routers. So one thing which was done was that these particular addresses, the private IP addresses, are not allowed and they need any packet which is destined for this specific range, private IP range, have to be dropped. Okay. Of course, we do have IPv6 addresses where there is no shortage of addresses, they can be used, but still not everybody in the world has migrated to IPv6. But certainly it is preferable to use IPv6 for peer-to-peer systems, because then we will not be facing this particular situation. And you will be able to talk to anybody directly. You can set up a connection to him because that's a uniquely routable entity if he is using IPv6 address. Now the three IPv4 address ranges are these: 10.0.0.0 to 10.255.255.255, and I am telling 8 because the first 8 bit is what will tell you the network address. So 10.0.0. is the address, and so technically you are going to have 256 cube. Those many addresses are private IP addresses are possible in this, and these are generally used by big organizations. So they actually allocate this private IP block inside their organization. When they need to communicate to outside, then only actually they have to figure out a method so that they essentially technically do what we call network address swapping or translation. They will do so that the communication, any machine from inside can go to outside world. They can also now even regulate because of this. That's where the firewalls come in. And of course, these were actually done even when your classless inter-domain routing was also not able to handle the shortage of addresses. Basically, CIDR allowed the reuse of class C addresses, and they can be converted into bigger blocks. Earlier, they were only one block size of a class C address can have at most of 256 hosts inside. Actually, there will be only 255 hosts which are technically feasible. So how the access will be happening to the internet? So there will be a private IP address in the network which is being used here, and there are actually various nodes. We have 4 nodes, for example, shown. They want to talk to internet. There is a server, so they actually all will pass through router because these IP addresses are not permitted to go on internet. As I told that in internet, a router will drop the packet having private IP address as the destination. So for example, connection will have to be set up. So this node tries to set up a connection, and this address goes as it is. So while returning, this guy actually has put in his private IP address, so that will become the destination. Okay. While in the forward direction it was a source, while in the reverse it will become destination. Internet router will drop the packet, and no response will be received. That's what happens if this router simply is doing routing, not doing anything else. So now we can actually implement some what we call network address translation for solving this particular issue. Okay, so for example, now this source is having a private IP address. So remember, this is actually from the same block. Okay, so this guy actually transmits the packet, and so this is going to be used the way it has been told in the earlier slide. This will be dropped at the internet. So what is done is we actually use a special router. We call it a netting router. So this will replace this address by translating this forward. When it's moving forward, the source address and source port will be modified by a public address. Maybe this public address will be 192.68.0.20. Okay. So once this is done, the packet will reach here. So this server will see the source address as this address, not 192.168.0.1, but it will see 192.68.0.20. So it will put that address as a destination. So this internet will not drop it, and this packet which is moving back will be showing, in fact in forward direction it will be showing this 192.68.20 as the source address, while in the reverse it will become a destination. The packet will reach here. Now this guy has to do a reverse translation, so it has to remember that from this source IP address and source port, I translated to which public IP address and public port. So this has to be maintained in the table. There is going to be a netting table because of that. Okay, so this netting table will say that the packet which came from the source IP address port number was translated to this. In the reverse, you do the same translation again. It is done, injected into the private network, which will then route this private IP and it will go to the destination. So in fact, you are using this IP address, but the outside world sees you as this 192.68.0.20. So this is the mechanism which is used in such a scenario when this private IP block is used. So a lot of peer-to-peer network will actually be seen as coming from this one particular IP address, but actually they are behind the netting router and they may actually be holding on a different IP address. But we need to just ensure that communication does happen uniquely without any disturbance. Now question is, if A is there, A has not communicated to anybody, and there is another node which is outside, and this would like to talk back to A. This would like to set up a connection to A. Can it do it? So if it tries actually sending a packet back to A, what is going to happen? Okay, so it won't go because there is no entry in the table. Table need to have a mapping. So in earlier case it was done because A tried to set up a connection, that time entry got created, and that entry will remain for some time. There is always a timer associated, and within that time if the reverse packet will comes in, those packets will be allowed. So A's only job was at that time to keep on transmitting in the forward direction so that this entry is maintained. Every time a packet passes through, timer is going to be reset in the mapping or NAT table. So static entry will be required, and this can mostly be done by the network admin of the organization. So you can make an static entry. So server actually is running inside, but you have to even say this is going to, if it is a web server, it's going to run on 80 port. You will receive on 80 port. So you will define public IP address and public port is fixed, and then mapping to an internal IP address and port is going to be fixed. So that's how you can actually run servers even inside. Okay, so we require a permanent net entry mapping the private IP to the server port address, private IP and private port, which is the server which is running the private IP, the public IP and port, and this will be maintained in the netting table. So this is how it is going to happen. In that case, if B communicates, A will be able to receive it, and there has to be mapping which is going to be something like this. It will say that for this IP address port number, communicate to this. So this is a web server request. So outside world will see this server as 192.68.0.32, but actually it is 172.31.0.26. Okay. And of course, whenever B is going to make a communication, there is a entry which is there, static entry. So this IP address of B is public IP address, so it can always respond back, which will just pass through. There is no net entry need to be created for this reverse thing. Okay, so this entry is going to be fixed, and this is what is going to be used. So while this packet is going, will be shown as if it is coming from here to this node B in this internet. So normally we will never use static entries. These are being created dynamically. Okay, because public addresses are very few. So if within your organization, within your campus, I have say 10,000 machines, I don't have 10,000 IP addresses. I have very few. So these are mostly need to be allocated dynamically for various machines which are inside the campus so that they can communicate to the outside world. Okay. So these are all dynamically allocation. Static entries are done only for some servers which are of important nature, and it's kind of a very precious resource. It's not easy to get it. So here you can actually see a node actually is communicated. It's being communicating to the outside world, and there is a response which is going to come accordingly back to him, and then this response is coming to the source node. So this was actually going with 172.28.0.5.40,000, colon 40,000. 40,000 is a port. This is a typical way that we actually write IP address and port number. We just separate them by a colon. Okay. So this entry is coming. Now another actually machine talks to the same server. What is going to happen? It will be given a different public IP address and port number pair. So you can see that for one it was given as 202.30.5.30, 40,020. For other one it was given 40,030. Only port numbers has been changed. So there will be many machines with many many private IP addresses, but there are very few public addresses. So normally these many private IP addresses will be mapped to few public IP addresses, but many ports will be used in this case. So ports which are going to be used will be much more in number than what are used here. Okay, so the product of number of few IP addresses into ports. Okay, so this and multiplied by many IP addresses into whatever the ports, they roughly will be equal. Okay, so we are essentially now using multiplicity of ports where the IP addresses are few by using this dynamically configured netting table. Now one of the important thing is that in netting table the entry can only be done when the connection is going from inside to outside, because from outside when a connection comes, the outside guy will not be knowing what is the inside source IP address and port number. That's a private IP block. Okay, it can't even communicate to that. It can need to have some public IP address and port. So these are dynamically allocated whenever the first connection is done, and normally there will be a timer. So I should actually keep a third field here, which will be a timer here. So whenever an entry gets created, there is a timer. Whenever there is a packet which goes into out, the timer is going to be reset. So for that entry is there, packet from outside to inside will be permitted as per this table. Okay, this table normally will have 6 fields: source IP address, source port, public IP address, which is being allocated by NAT, and public port also allocated by NAT. This is server to whom you are communicating its IP address, server port, and then there is a timer. Now we need not fill up all the entries whenever the netting is being done. So based on that, how many entries you actually fill up, there are various kind of netting mechanisms. They have been classified in various categories. So first one is a full cone net. So in this case, whenever a packet from inside to goes from inside to outside, we actually make an entry for source IP, the source port, the correspondingly what is the public IP being allocated by NAT, and allocated public port on the public interface side. But then these remaining 2 entries, what is the destination host and which is the destination port, that is not being maintained. That's a star. As a consequence, when the reverse side the packet is coming, these cannot be verified. You only just look at if it's coming from this public IP address and public port, replace them by this. The source host IP address and port numbers you don't bother. Okay, so this kind of NAT is known as full cone NAT. Now the way it actually operates is very simple. When a request goes from source to for host 1, the entry is going to be made. So these 4 entries will be there. This will be star star. So H1 now can respond. So when H1 comes back, it won't be checking for H1's IP address and port. It will just look at what's the public IP address and port for which the packet is coming, and it will do the address swapping and it will go into S. But because I am not checking the host IP address and port, even host 2 and host 3 can also communicate back to the same source. Okay, they somehow need to just figure out that for this source, this is the public IP address and public port which is there, and they can then actually send the UDP packets back to the source. They can't do TCP because TCP works in a slightly different way. TCP you have to set up the connection in the beginning. Okay. So why only UDP? So netting routers normally are also firewalls, and they allow only certain kind of packets to go through from in to out or from out to in. So these are going to be in firewall rules. Okay. So we use IP tables in, for example, in any Linux machine for doing this job. For TCP frames, normally there is a sink frame which is transmitted. So when IP packet comes in, we actually look into the payload. These firewalls look into the payload, whether it's a TCP packet or UDP packet, and they analyze the UDP or TCP header, and based on that take the decision. So we can say the sink packet SYN can only go from in to out. So it means connection can only be initialized when somebody from inside is trying to communicate to outside. So normally sync from outside to inside will not be permitted because of the attack issues. Or of course it can be done, but in that case you require a static entry. Otherwise this guy will not be having entry, it can't communicate back. Okay. So only for a static thing it will be done. For in to out normally will be the connection, and we can actually have regulations like only part of the network can communicate to another part of the internet. All those kind of rules can be done. Okay, it's a basically default is you deny everybody, then you start allowing specifically for to be on the safer side, to be more secure. For UDP, normally in to out will be permitted, because out to in when it comes, of course, he does not know to whom you have to pass it on unless there is an entry in the table. Okay. Out to in will only be permitted, make sense if there is a netting table entry. So it will only be permitted if the netting table entry is there, otherwise it will not be. For TCP, permission table as well as the NAT table both should actually allow the things to happen, then only it will be possible to set up the communication. TCP also is actually permitted mostly in NATs. It's not that we actually, for example, in IIT Kanpur use a netting router. From inside when I am setting up a TCP connection, so sync is permitted only from in to out, but when sync is being forwarded, that time NAT entries also gets created. So in the reverse, when the packet is coming, okay, then those TCP frames or IP packets will be permitted after being viewing into this and will be passed on to the source. And if it is a full core NAT, somebody else can also set up send a sync entry back, but that sync will not be permitted because there is also a firewall rule which says sync cannot come from out to in. So nobody from outside can set up a packet, but with UDP this will be feasible. That's why in the previous slide, previous to previous slide, when there were two hosts, they were also able to communicate back, while from inside only for one particular host the UDP packet was sent, and it was using the same table which was created for the in to out connection was used by the other two hosts for out to in connection. Okay. Now whenever the UDP thing is done, that actually means you are creating a hole, and through this hole even other host can send the information back. So in fact we call it a UDP hole punching because of this. Okay. Now the question is how this host, so inside machine has client has communicated to some server, how some other host will know that what is this netted IP and public IP and netted public port for this particular client. Okay. So there has to be some mechanism by which this has to be done. So one way is that we can actually have a protocol called STUN protocol. So client will now talk to server, and server will figure out what is the corresponding public IP address and port from which the messages come. Okay, it will actually put this in the payload and send the message back. And when the message comes, the destination address will be only replaced by this address, but the payload will remain as it is, and payload contains this address. So this guy can actually figure out what is the public IP address and public port has been allocated by NAT to me. Okay, and of course then this has to somehow tell this particular host that which particular netted IP address and netted port has been allocated to me. Then this host can actually communicate back via this netting router to this client. Okay, so this is actually slightly tricky, but that's the way it is. Okay. Now let's look at the second case. So previous one was full cone net. Now we have an in network, we have an outside network. Inside is using private IP block. Now the new entry we will also be storing what is the host IP address to whom the connection was set up by the client from inside. So I am going to make this entry. The port I am not bothered. The moment you do it, now there is a problem. When this host sends a packet back, I am going to check from which host IP the packet is coming. If it is not coming from this host, it can be coming from any port, does not matter. But it has to come from the same IP address. If it comes from the same IP address, I will permit, otherwise I will drop. Consequence, this host 2 cannot send the message back to this client. Unless this client decides I am going to send a message to this host 2, for which maybe a different public IP address and port can be allocated, or maybe the same one. And when it sends this information to this, there is going to be another entry which is going to contain this host's IP address, corresponding public IP and public port. And then when it is going to communicate back, then communication can happen. So only those hosts can send you the information, those IP addresses can actually communicate back to whom you have communicated. Nobody else can do it. So it's not a full cone net, there is a restriction. We call it an address restricted cone net because of this. So address has been restricted to the one to whom the inside client has communicated. Okay. This is the second kind of net, so this is a more restricted. We can further extend this. We can say now not only I am going to actually put host IP, but I will also put host port also in the table. Now it's very restrictive. Even if you communicate to host 1, to whichever port you have sent the signal, send the information, only that port can communicate back, no other port. So even other ports on this host cannot come. So that becomes a port restricted cone net. So other hosts also can do the same. And interestingly, when a source is communicating to other hosts, it can use same public IP address and same public port. So this kind of a reuse which can happen. Same entry can be there, but these entries will be different. But only problem is this guy host 1 and host 2 both are actually now contending for the same public address, public IP and public port, and inside if there is a common buffer, there is a common buffer for the source. So they may start competing for the buffer for this particular source. Okay. So people actually even have built nets which are even more restrictive. Okay. So these nets, essentially only condition which you will do is that these public IP address and public ports cannot be reused. If it is used for one host H1, something else has to, some other pair has to be used for H2. At least one of them have to be different. Okay. So such kind of nets are known as symmetric nets. These are very difficult to actually, there is a UDP hole punching cannot be done. Okay. So because other host cannot communicate back to you. So symmetric nets are much more safe, and these are also being used, but these are also require larger table and larger decision making process whenever the packets are passing through. Now how the P2P clients will traverse through this netting routers. So that remains a challenge. So let's look at the ways and means by which this can be done. So let's look at host P1. So host P1 is now communicating to the internet. It is having a netting firewall. We can do it through a stun server. Okay. So stun server is very simple, that P1 will send a packet to the stun server. Stun server will actually now look at, will see this IP address and public port, public IP address and public port as the source of the packet. It will just put that thing in the payload. We call this address as reflexive transport address. Okay, so that's what is going to go in the payload and it will be sent back to P1. And so P1 will know what's the address which it has. Same way P2 can also find out its reflexive address, which is the address allocated here. Okay, so once this is there, somehow these P2, if it knows what is the reflexive address for P1 and P1 knows what is the reflective address of P2, so any one of them actually should need to know. Only if P1 knows about what is the P2's reflexive address, it can just communicate the message to this and this will get routed to this particular IP address. Okay, and since this has already created the entry, netting entry via Stun server, and this is a full cone net, so the request, this particular address will be seen as a host. So this request will be permitted to go into this system. So even if it is a port restricted cone net, in that case, the both of them need to know each other's. At least one of them, actually, for example, this guy knows this address, so this guy will directly communicate to this address, but the entry will not be there. That's a problem, so it will not be allowed. So this guy need to communicate to this net one, this guy need to communicate to this net 2's public IP and port. So, and both of them will know the entry, and after that if they start communicating, that will be permitted, because now both of them have the entry in their net tables. So even with port restricted cone net, it is possible to set up this peer-to-peer connection between two peers who are behind nets. Both of them are in private IP. They don't need to actually have some third-party router to route their messages to each other. So this is one way to traverse the net. This actually works beautifully with full cone net, address restricted cone net, as well as with port restricted cone net. All of them actually can be taken care of. Both P1 and P2 need to find their reflexive transport addresses through a Stun server using that, and then somehow they have to communicate to each other. So which can be done through messaging, because they can actually keep on pulling the information from, because they can always set up a connection to somebody outside. So somebody who is there on the public IP and he is holding their addresses, they can deposit their addresses, and from there the exchange can happen. Okay, for their user ID to that particular public node ID to public IP address, they can always put in a repository. So this guy also can do, and then they can find out from user ID the node ID, and from node ID what is the corresponding reflexive transport addresses, and they can do a peer-to-peer communication. Only thing, these two guys need to ensure that the UDP hole is punched in both the netting firewalls, because of by periodically sending the packets out. The moment they stop doing it, they will be unreachable after that. So one of the ways is that both P1 and P2 will publish their reflexive transport addresses as their address to the neighbors, and neighbors will update their entries in their routing tables. In fact, the guys who are holding P1 and P2 in their routing tables, okay, so these P1 and P2 need to keep on telling them what's the corresponding reflexive transport address they have, so that these guys who are actually holding P1, P2 in their routing tables can keep on updating their entries, and they can communicate back to them. So they can initiate the connection to P1 and P2. Okay. So P1 will send message to the other P2's public IP address and port, as I mentioned earlier, and P2 will do the same. Okay. And any node having and every node need to do something, look into routing table, and all the entries in the routing table which are behind net, just keep on asking them to keep on updating their current reflexive transport address. These reflexive transport addresses can also change. Then they are not static. So now it is something else. Next time you send, by the time that entry, then router decided to allocate you something else, they can be dynamically changed. So these need to be updated. So otherwise your network will not operate. So they will be just going out of the network for some point of time, and they will ultimately come back in, of course. And so far we have assumed that symmetric net is not there. So how to take care of symmetric net? Stun will not work actually in that case. Stun only allows the peer to figure out what is his reflexive transport address and somehow communicate it to other guy, and they both can talk. But in symmetric net, the problem is that you have to essentially, the only way it can be done is when both of them, as I mentioned earlier, that P1 is going to talk to P2's reflexive transport address, and P2 also does for the other guy simultaneously, and they both get the entries done. And since in the reverse path it is going to come through a different same transport, same basically public IP address and port numbers as they have sent the packet to, they can accept. But the problem is here is that in a symmetric net, they have to identify what's their public IP address and port number. They can't do this actually now, because for that they have to go to some Stun server, And when the instance server for that particular path, the IP address and public IP address and port number is allocated, this cannot be used for some other communication. Okay. So it cannot be used to communicate to some other host because it will be allocated different public IP address and port number by the netting router. So it actually fails in case of symmetric net. So in that case, we need to go for turn server. Okay. Basically, it's a relay node. Okay. So netting traversal can be done through a relay node. So in this case, the turn server will be there, and you will create a connection to the turn server, and turn server on your behalf will allocate you a public IP address and port number, which is on your behalf, and this number will be told to you. So turn will now keep a record that this particular public IP address and port number has been assigned to for P1. So whatever is the public IP address and port number coming from this symmetric net. So this is mapped to this. So when you are going to tell to somebody, you will be telling somebody else as this is your IP address 202.141.40.192:8520. So when P2 want to communicate, it will send on this particular IP address, and turn in turn will now reflect it back to the P1. So it is going to act like a reflector. Okay. Now that's a pretty heavy load. If there is a video or something, this is going to now do a lot of relaying on your behalf. So this is not that easy. So normally this is the paid service which is done. It's not a freely available thing. While you can find out a lot of instance servers which are freely available because they don't put much load. Just go and query what is your corresponding public IP address and port number. So this server acts as a relay. Okay. So on your behalf. So that's how the symmetric net is actually handled. And of course, it also does take care of the firewalls automatically because connection is being initiated from inside, and on that setup connection only the reverse path traffic is coming, and forward is also going on that. So there is no need to worry about what is permitted, what is not permitted. So now another way things can be handled when, for example, there is no netting router, there is no firewall. So they say there is no traffic directly, no UDP or TCP packet can directly go from in to out. So there is only going to be a web proxy. You can make a HTTP connection from your browser to the web proxy. It will do on your behalf a web proxy, a HTTP connection to the outside server, and the return path, the information will come back. For GET, this is fine. GET only you send a URL, and reverse they will get a payload. So I can't use GET actually because I also need to send as a peer need to send information to the peer who is outside. Okay. So in that case, then there is a problem. So let's see how this can actually get solved. So in fact, on the outside, as I had shown in the previous slide, I had shown as a web server. So I don't need a web server because I am now transacting information, okay, which was going normally as a UDP message or a message over a TCP thing. So now this will be going through HTTP transport. So there is a web port which is available. So there is HTTP protocol has to be implemented by some peers. We call these peers as proxy peers. So they are a special category. So I have to search for some proxy peer and essentially communicate to him. So he will now make an entry that for me he is acting as a proxy. So what I will do is I will now use normally a connect. There are actually three modes of communication in HTTP: get, post, or connect. So get is not used because you can only retrieve the information. With post you can dispatch something. In a response you can retrieve something also. Only thing you have to have a timer. I do it now. Then after 1 minute again I will do it. So by the time whatever is collected by him, collected by me, I will send it to him. Whatever is collected by that proxy will be sent back to me as the payload. So, but then this periodicity also need to be, I need to keep on adjusting so that there is not much backlog in the queue gets created. Okay, so that proxy peer will have a HTTP interface through which I will be connecting, and I will be now publishing the IP address and port number of this proxy peer as my IP address and port number. We call it I will actually tell this is a proxy peer address. So all other guys who want to send something to me will send it to him. It will be encrypted so he can't decipher it, but he will route it back to me through HTTP. This is technically HTTP tunneling, which I am actually doing. Okay, so there is somebody else who is working on my behalf, who is on the publicly on the internet. So the worst case scenario, this is always going to work. This is how actually earlier even Skype used to work. Okay, and now we have also this connect mode. Connect mode creates a continuous pipe, so I need not do the timer based thing. I can, whatever things come, I can keep on transmitting, and this guy can keep on sending whatever is coming for me. There is a continuous pipe. This was basically being created for WebSockets or for direct peer-to-peer transaction on a continuous basis, streaming basis is for that. So now we can even use this. This is far more efficient than doing post and then adjusting timer again and again, sending the request. Okay, setting up a new TCP connection. So that will no more be required actually. And of course, as I told, whenever the post method is used, we need to periodically send the post request, so that I am going to send with that post request a payload, and whatever the other guy want to send back to me will come as the payload back to me from the proxy peer. And when the messages are received, the proxy peer will receive the messages on my behalf from other peers, and that's what I will get from him in the return, in the response. Only thing it requires now a timer. After what time I have to send a post request. So this need to be continuously dynamically adjusted so that I don't have the buffer overflow at both the ends. Okay. So this will be one additional requirement which is going to be there. So in fact, as I told earlier, this is what is basically HTTP tunneling being done to the proxy peer. So in today's lecture, we actually have looked at how the private IP problem can be resolved in a peer-to-peer system. So almost all peer-to-peer networks, even like Skype or everybody, is now actually operating either with a NAT, UDP hole punching, and worst case they then switch over to TURN or to HTTP tunneling. All three modes are normally supported, but normally most of the organizations nowadays do allow NAT or maybe any kind of NAT, but the HTTP tunneling only based organizations are very few, but if they are there, we need to provide HTTP tunneling for that. So with that, I actually end this lecture, and we'll look at the next topic in the next video.